Okay, so this will be the second video to accompany that first one, talking about the rest of the periodic trends that you guys are responsible for. So we just finished atomic radius in the previous video. This one is for ionic radius, which is very similar. The trend is still the same. It'll increase to the left and down the way the other one did. But this one's a little bit different in terms of it's really not about entire groups or families. It's more about single atoms or relationships between one atom and another. So if I talk just about a single sodium atom will have a certain size like it does right here, where the sodium atom is actually larger than one that had a positive charge. As you take electrons away, and there's the same number of protons in the center, that Zeph value is going to be stronger on those outermost electrons, and so it pulls the radius in so that it in fact gets smaller. Now, the opposite is true for ones that are going to become negative. So for like chlorine or chloride, for an example, chlorine will actually be a smaller atom, but when it gains electrons towards the outside of that atom, it's going to become much larger. And so that Zeph will still be the same, still 17 protons pulling on all those electrons, but it will pull less strongly on that next electron that's added. And that's what the difference is between these, between ionic radii of the same element. And so here's kind of an example. Sodium would be really much larger, and if you take an electron away, that Zeph value will be pulling on fewer electrons, and so the cation, the negative ion, or excuse me, the positive ion of the sodium would actually be smaller. Whereas the opposite, an anion is one that gains an electron and becomes negatively charged, and so it would actually become larger because there's they're the same number of protons in the nucleus, same Zeph, but it's pulling on more electrons, so that last one is effectively held less tight. So where this becomes more important and more relevant is when it comes to what are called, or what are termed isoelectronic ions. So isoelectronic ions are ones that have the same number of electrons, so they have the same electron configuration as something else that has the same number of electrons but a different number of protons. So they're different elements. So like down here on the bottom, we've got sulfur. I'm circling sulfur down here. When it's an ion, S2-, it only has 16 protons in the nucleus. Its atomic number is 16. But if you compare it to argon, argon has 18 protons in the nucleus. If they have the same number of electrons, meaning 18, sulfur gaining 2 from the 16 would have 18, argon is element number 18, argon will actually be smaller because, once again, the Zeph value is dictating the size of those elements, making them smaller. A quick way to remember this, especially about the anions and cations, is a goofy little memory trick here where we talk about giant ants. So anions could be thought of as ants, you know, giant anions, they get larger, giant ants. And then cations, which are the positive anion or positive ions, will be tiny. So those are fingers holding up a tiny little cat. One other way to remember between the two is that the word cation actually has a positive charge in the center of it with the T. So that might help you remember that anions are negative and cations are positive. Also, another one is we think negatively about ants and we think positively about cats. Now, there's a lot of people that argue with me because they can't stand cats, but that might help you kind of remember which ones are which. So another trend is ionization energy. That's the amount of energy required to remove an electron from a gaseous atom. So you're taking an electron away and making something more positive. The exceptions for ionization energy are the same as Zeph. In fact, the entire trend of this is the same as Zeph. It increases as it goes up, and it increases as you go right across a period. And so the larger ones will be up there in the fluorine, chlorine, neon range, and then down here in francium will be your smaller values. Once again, the exceptions are going to be the same. Now, I've written all over this. It's kind of a disaster. And I'll kind of skip through those in the word form. But the exceptions for Zeph are, like I keep saying, the same as they are for ionization energy. So those exceptions would be at the sp boundary right here, where you go from s to p, and right here where you have a doubly occupied orbital. So you have an electron here, an electron here, an electron here. When you doubly occupy by adding that 8th electron, as you would in oxygen, that last electron will be a little bit easier to remove. And so the amount of energy necessary to remove that electron would in fact be less. And so what I'm trying to tell you is that these, is that ionization energy and Zeph are are the same. They have the same exceptions and the same trend. And that can be seen here. Now, this is a mess, this chart, I know. But if you look at the chart carefully, this is the first period right here, hydrogen to helium. And this is the second period here, and third period, and so forth. Those are each of the periods being shown here on the graph. And if I look at the values for ionization energy, from hydrogen to helium, it gets larger. From lithium to beryllium, it gets larger. And then it goes down a little bit at boron. That's because those s orbital electrons are repelling the p a little bit. As I go across that p orbital chain right there, those sets of orbitals, boron, carbon, nitrogen, and then look, there's a little dip right there at oxygen like I was talking about. And so it does, look, it repeats the same thing in the third energy level with phosphorus and sulfur and with magnesium and sodium. And so what I want you guys to understand is those trends that I showed you, those exceptions that were in Zeph, need to be also written in your periodic table flip book for the same exceptions for ionization energy as well. So, yes, ionization energy, I don't need to explain all that. It's kind of the same. This, though, is a little bit different. You can have multiple ionizations. So you can have +1 and then lose another electron +2, another electron +3, and so forth. So there can be multiple ionizations of a single atom. And this is really relevant when you talk about something like aluminum. So here's the aluminum atom, aluminum gaining, or losing rather an electron, and then aluminum losing 2 electrons would be its second ionization energy, and then of course becoming a 3+ charge at the end, it would undergo its third ionization energy. And notice that they get larger because these electrons are going to be closer to the nucleus, higher Zeph values, more energy to remove them. And you can see that in this chart right here, which I think is just great. Let me see if I can move it. Yeah, there we go. So if I'm looking at this chart here, this is a chart of first ionization, second and third ionization, even fourth ionization energies of 4 different elements from period 2. And so, or actually period 3. But if I look at this, let's see if I can change that color. Can I change the color to? Sure, we'll try yellow. So look at sodium. Sodium's first ionization energy is 496. Look at the second ionization energy of sodium. It goes from 496 to 4,562. That's a huge jump. That means that sodium is really only going to lose a single electron. It requires too much energy to remove that next electron. The reason is because that's a core electron. It's no longer a valence electron on the outside of the atom. And so sodium and all those group 1 elements will actually form atoms or ions that only have +1 charge. Look at magnesium, 738, 1451, and then boom, 7,000, huge jump. That demonstrates that magnesium will actually only be a 2+ charge. So it's only going to effectively lose 2 electrons. Look at aluminum. The jump is at the 4th ionization energy, so it'll easily lose the 1st, 2nd, and the 3rd electron, becoming 3+ charge. And then once it gets to that 4th, there's no way it's going to lose that much energy or gain enough energy to lose that 4th electron. By comparison, if you look at the last one for silicon, silicon has pretty much the same change all the way across, 7, 15, 32, 40. There's no huge jump that says it's not going to lose that electron. That's one of the reasons why we told you guys that it's kind of like plus or minus 4. It can kind of go either way, but in reality, ionic compounds usually do not have group 4 elements in them, not unless they're a polyatomic ion, and that'll be a discussion for a later date. One other one to talk about is electron affinity. Electron affinity is the amount of energy that's giving off or absorbed when an electron is gained by an atom. And the trend is the same. It increases this way and over. But if you look at this, there are so many different exceptions that we're not going to have you responsible for any of those. All you've got to know is the trend here. So it says electron affinity, very challenging topic with lots of exceptions. We'll do some of them in AP Chem, but you don't need to do that now. Electronegativity is kind of our last trend here. Electronegativity, once again, the trend is going to be up like this and to the right increasing. The highest value being fluorine. These are things that pull electrons to them when they're in a bond. So if I had something like hydrofluoric acid, hydrogen and fluorine would share a pair of electrons. Fluorine will actually pull these electrons toward it with a higher force than will hydrogen. If you compare, the value right there for fluorine is 4.0. The value there for hydrogen is 2.1. There's a large difference. So fluorine will actually pull those electrons towards it. That's the definition of electronegativity, and the trend is the same. It increases as you go up and to the right as we did before. So yeah, this is just more of the same. Just remember that the largest ones are going to be up here with fluorine, electronegativity, and the slowest, the smallest would actually be francium. So elements that tend to have high electronegativity are going to be on the far top right of the periodic table. So those are ones that are nonmetals. And then the ones on the left of the periodic table are going to be the ones with lower electronegativities. They tend to lose electrons. Those are going to be your metals. So here's the summary of all the trends. If you look over here on the bottom, those are just going to be atomic size getting larger that way. And then all the electronegativity, electron affinity, ionization energies F, those are all going to be increasing. Now, an easy way that I taught myself to remember this is if I draw an E like this, and I draw an E with arrows like this, all the ones that have E's are going to go up and to the right. Whereas for atomic size, which is really radius, the radius goes like this. So for atomic radius or for ionic radius, they're going to increase to the left and down. And so maybe that'll help you guys, I hope. Hope tomorrow's not too bad without us. We will miss you, and I'm posting this video as soon as I can get it rendered on YouTube.